Welcome back. Let's do a steady state sinusoidal response via the transfer function h of s. Okay, if you have a transfer function, you can use that to determine the sinusoidal steady state response. So we're given this transfer function h of s is some output signal v0 over vg or v generator. So this is how, a transfer function could be any output over any input. So these have just been chosen for us as our transfer function. And some genius did the circuit analysis similar to the other problems that we did, and they came up with this transfer function. Okay, so they looked at the circuit already, like we did in some other problems, and they did a bunch of algebra, and they came up with this guy. Then somebody wants to know, well, what happens if I flip this switch and turn on the time domain input signal specified by this function here? Okay, so somebody walks in and turns on your anti-asteroid laser, hooks it up to power, flips the power button, and then all of a sudden this 12.5 cosine 8000 t signal is applied to the input. That's what's given, is these two things are given. So we want to find what is the output at steady state. After the initial effects of the switch flipping, after those die down and we just have a sinusoidal steady state, what is that sinusoidal steady state? We did sinusoidal steady state in chapter 9, right? And this seems like a real roundabout way to do the same thing. And it kind of is, but it's fun to have, or it's good to have these transfer functions, right? And so we don't have to do any calculus, and we can also use them to find the steady state response. And there's other reasons for this. Really, we're just trying to get familiar with transfer functions and the plus and all of this stuff. Okay, look, here's what we're going to do. These are from the notes. This is the math that we're going to use. This is our input signal, a general form of an input signal. This is given a transfer function. If we solve it at j omega, we'll end up with a magnitude and an angle that we can plug back into. Oh, I'm missing a bracket here. Oh no, there it is. It's on there. We can plug back into the output signal and get our answer. And then what we're interested in is this part here, right? After the bumps from flipping the switch have died down, after the transient response has died down, what's the sinusoidal steady state response? So our solution, we're just going to use the sinusoidal steady state h of s expressions that I just showed you from the outline note. So the general form of an input expression, just what I just showed you, is x of t, some input expression is given by amplitude a cosine omega t plus some phase shift phi. So what that means is, for this particular problem, a is 12.5, omega is 8,000, and phi is 0. Then we could solve h at j omega, right, just by plugging in j omega into this h of s thing, right? H of s is this transfer function. It's going to be h at j8000, because omega is 8,000. So plugging these guys into here, you're going to get 10 to the 4th j8000 is s, plus 6,000. This stuff up here, just with s being j omega, s being j8000, and then you get j8000 squared. That's s squared plus 875 s, which is j8000, plus 88 times 10 to the 6. Oops. Don't know if I need that. I don't need that paren, but I'll put another one in because I can't erase it. So what is that guy? This monster here is just a constant, right? There's no omegas in there anymore. So it's going to be simplifying it down a little bit. You could punch it into your calculator. At some point you got to. Sometimes it's good to make it a little simpler before you stick it in your calculator, right? This guy here will be minus 64 times 10 to the 6, right? Because j squared will be minus 1. That's the minus. And then the 8,000 will be 64 times 10 to the 6. And then this thing in here, this guy, this is going to be j 7 times 10 to the 6. And then our constant, this guy that's just hanging along for the ride here. That's that. And then you can factor out this 10 to the 6. They all have 10 to the 6 in there. So you and you could pull out a couple of zeros out of this. So you get 10 to the 7th, j8 plus 6 over, and then pull the 10 to the 6 out of the denominator. You get 10 to the 6, j7 plus 24. Now that's a little bit friendlier to stick in your calculator. And you're going to get 3.2 plus 2.4j constant, which in polar form will be 4 angle 36.9. It's a constant like we did in chapter 9, phasors, right? So we can do this kind of stuff. And this chapter likes to express this phasor notation in exponential notation. So it's 4 e to the minus j 36.9. Okay, so we have all the pieces that we need. We have the magnitude, the phase angle, all of these little bits and pieces that. So just to isolate them. So the magnitude of h of j omega is 4, and this phase angle here, theta sub omega, is 36.9. And then we can plug into our general solution y of ss of t. So our general solution y steady state of time, general solution is a magnitude of h solved at j omega times cosine omega t plus phi plus theta of omega. Ugh, yuck. So in this case, our output signal of interest is v0 of t. So plugging this stuff in, A was 12.5, and h of j omega is 4, and cosine omega is 8,000, t, phi is 0, theta sub omega is 36.9. That's the answer. So, you could write it a little more simple. It's 50 cosine 8,000 t plus 36.9 volts. That's the steady state response. So there's a let's see, if you wanted to graph all of this stuff, so there's v of g, which is a cosine function. So it's 0 until the switch is thrown, and it jumps up to that. Then what is the output signal as a function of time? What does that thing do? Well, at steady state, at some point in the future, it just becomes a sinusoid. But there is a transient response that we're ignoring, and we don't know what that's doing, but who knows what it's doing. But okay, so it's transient, and then eventually it settles down and it becomes steady state. That's the concept that we're interested in. And we'll solve one where we're going to look at the transient response. And the reason I don't like to mess with them too much is most of the time they don't really seem to matter. Now, they don't affect the signal that much. Now, that doesn't mean you can ignore them in real life. Like transient responses can break stuff, right? Like in the book, in the practical part, there's always a practical problem at the back. They talk about surge suppressors, right? Those little things that you get that you plug your computer and stuff into, because supposedly there can be transient responses in the power grid. There can be these spikes from a lightning strike or from something blowing up or whatever. You could produce these transient responses, and that could break your sensitive electronics, supposedly. I am personally, I'm a little bit of a skeptic about that, because there's these if you look at an average typical electronic device, there's a zillion frickin', billion transistors. There's a simple device, I forget what it's called right now, that'll suppress voltages. It's like one tiny little silicon device that costs a millionth of a cent. So I personally don't think that any manufacturer would leave their electronics vulnerable to voltage suppresses, voltage spikes, when it's so easy to prevent in the power supply of the device. So that's probably a personal expression. I've never broken very many things. I have a generator in my house. And when the power was out in the summer, we would turn that thing on. It turned on the whole house, and nothing broke. Anyway, there's transient responses, there's steady state responses. We're going to look at a problem next that does everything we've done in the other problems, right? The other problems, there's this one of steady state, and there was some other where we were deriving S's. Now we'll look at the whole thing next. All right. Bye.